Okay, so a 20-foot ladder leans over a 12-foot wall so that 5 feet project over that wall, and the bottom of the ladder, we're told, is being pulled away at 5 feet per second. And we're interested in how quickly the top of the ladder is approaching the ground. So why don't you pause the video and work on this problem and see what you get. All right, assuming that you give it a go. Again, this is a related rates problem, and typically, we want to get a picture going as quickly as possible and start describing things and start laying out what this problem gave us and what we need to find. So we're told this. We're told we have a 20-foot ladder. We have a 20-foot ladder and a 12-foot wall, and 5 feet of it are going to be projecting over the wall. So let's see. Here's our ladder here, and this is 12 feet. All right. And then let's put some ground. Let's get some ground going here. And we have a 20-foot ladder. So we have this 20-foot ladder, and some of it's going to be projecting over the wall. Let's see how straight we can get that. All right. We'll go with that. Sure. So we're told that this whole ladder here, oh, I want that to be white. Here we go. This whole ladder here is 20 feet long. And we're told that 5 feet, this first kind of length here, 5 feet, is going to be projecting over this wall. Okay, so what else are we told? We're told that it's pulled away at 5 feet per second, and we want to figure out how quickly the top of the ladder is approaching the ground. So we need to get kind of some notation to describe both of these things still. So we need to figure out how to describe this top of the ladder here, this point. We can call this length, let's call it y. So let's call this length y. This will be y. And then we need to also describe it being pulled away at 5 feet per second. So this ladder is getting pulled away. And how is that? Well, we can throw an x on this. We can describe this length here. And then as we pull away, this will be dx dt. Dx dt will be 5 feet per second. So as this gets pulled away, this will be dx dt. So x changing with respect to time is 5 feet per second, and we're given that in the problem. So let's see, do we need anything else? Well, I think maybe one thing to consider too is, okay, we're told 5 feet are overhanging this wall here to start off, but will it continue? Will that same 5 feet continue as we pull away the ladder? Will that same 5 feet be overhanging the wall throughout this whole time when we're pulling away the ladder? Well, no. As we pull away the ladder, this length that overhangs the wall is going to be changing. So that's going to be changing with respect to time too. So this we're actually going to call, here, let's do a different color. We will call that P for projecting. That's the amount projecting over the wall. And it's going to be changing. And then if that is P, then what is this length here from our ground up until where the ladder is going to be projecting over the wall? Well, that is 20, our full length of the ladder, minus P, the amount projecting. Okay. So I think that's everything that we need to describe this situation. And again, what do we ultimately want to find? We want to find how quickly the top of the ladder is approaching the ground. So we want to ultimately find this. We want to find how quickly, we want to find what dy dt is, how quickly y is changing with respect to time. All right. So that's everything. And again, with related rates problems, we've been doing a ton of examples. We want to then describe and relate kind of these variables. So we need to get some relationships going between them, end up differentiating and plugging in some information to ultimately find we're after dy dt. So how could we relate these variables here? And I think a good thing that I see right off the bat are some similar triangles. I see this triangle, this big triangle here. Let me put that in purple. I see this big triangle here, this big triangle here, and I also see a smaller triangle, and we can relate these through similar triangles. And it looks like we can get a relationship between y and p going here, and that would be awesome. So let's do that. Let's write out some similar triangle information. So similar triangles. We'll put that right here. So we can relate y over this hypotenuse. So we have this, we have y over, and then we have p plus 20 minus p. So we have p plus, and we'll put that in this, so 20 minus p, okay? So that's, again, that's our relationship of that larger triangle between its side length and the hypotenuse. And then if we're going to use similar triangles, the other triangle that we're going to be relating to is the smaller one. And I'll just keep that in orange here. That's going to be this smaller triangle. So that's going to be, again, under similar triangles, that'll be 12 over its hypotenuse, which is 20 minus p. So this is 12 over 20 minus p. 20 minus p. All right. So again, we have some relationships. This is between y and p. And what's cool is I think a good next step would be, okay, let's get all of these p's on this right-hand side, differentiate with respect to time, because then we'll have dy dt, and then it will tell us what other information we need to go out and find. So let's do that. Let's get all the p's on this one side and differentiate. So real quick, p plus 20 minus p, well, that's just 20. And then multiplying by 20 on both sides, we're going to have 240. So here, let's write this out. We have y now is equal to, and we're multiplying both sides by 20. So we're going to be left with, this is going to be 240 times, and we'll bring this guy upstairs with a negative exponent to make differentiating a little easier. So this will be times 20 minus p, 20 minus p to the negative 1 power. And now what we're going to do is differentiate both sides with respect to time. So let's do that. So we have dy dt. And again, that is what we're after. That is a good thing. We're after dy dt. And now on this right-hand side, by the chain rule, we'll just put it all in orange now. By the chain rule, we're going to have negative 1 come out front. So this is negative 240. And then we keep the inside, 20 minus p. And we decrement the exponent. So it's negative 2. And then the derivative of the inside with respect to time is going to be negative dp dt. Okay. So this kind of tells us, all right, we got to go find out what p is, and we got to find negative dp dt. And then we also have to remember, okay, we were given some other information. We were told how x is changing with respect to time. So that tells me, okay, if we can set up a relationship now between x and p, that might give us the remaining information that we want. So how can we relate x and p is the question. Well, over here, I mean, just looking at this orange triangle here, it looks like we can relate those just through the Pythagorean theorem, which would be great. So let's do that. So we find by the Pythagorean theorem, 12 squared plus x squared, and that's equal to 20 minus p squared. So that's 20 minus p, and all of that is squared. That's just the Pythagorean theorem. And now what we want to do, because again, we have this information, they gave it to us. We can differentiate this with respect to time, and maybe we can then substitute this value in and find some other information. So let's differentiate this with respect to time and see what we get. So again, this is a constant, so that's going to be 0, and then we will have 2x, and then times dx dt, so just some chain rule, and that's equal to, on this right-hand side, we're going to differentiate with respect to time again. So we bring the 2 out. We'll just keep this in white. So 2 times 20 minus p, and then that becomes a 1 as the exponent. And then the derivative of the inside is what? Well, it's going to be negative dp dt. Okay. So now we kind of have, we've exhausted our derivative information. We can now substitute our 5 in for dx dt, but we need to find what x and p and dp dt are. And how do we do that? Well, with other related rates problems, remember, we're given some information about a particular moment in time. And this is the same thing that's going on with this problem here. We're told what? We're told at a particular moment of time, 5 feet of this ladder is overhanging our wall. So let's draw out our particular moment that we were told about. So here's our wall again. This is 12 feet. And here's our ladder. Here's our ladder. And then here's the ground again. There's the ground. Okay. And again, this whole ladder here is 20 feet, but we're told 5 feet start overhanging it. So at this particular moment, 5 feet of this ladder is overhanging the wall. And if our whole ladder is 20 feet, then this remaining length here is 15. Okay. And this is still going to be described as X. And what is this 5 under our notation? Under our notation, we said that that length here was P. So a 5, in this case here, P is going to be 5. All right, so we found P, and again, we're just trying to fill in the information that we have left. We need to find what X is. We already know what dx dt is. We just figured out what P was, and now, we maybe need to solve for dp dt. So let's first figure out what X is. We can find X just through the Pythagorean theorem. So grabbing some space, we have X squared plus 12 squared plus 12 squared, and that's going to be equal to 15 squared. Equal to 15 squared. Solving this out, we have X squared plus 144 is equal to 225. And then 225 minus 144, that should be 81. This is equal to 81. And then taking the square root of both sides, we have X is equal to plus or minus 9. And we just want the positive length here. So X is going to be equal to 9. So we found X. We have P, we have dx dt, so that should be enough to solve for dp dt, negative dp dt. So we said that we're going to have 2. We found that X was 9. We were told dx dt is 5. And then on this right-hand side, we have 20. We have 2 times 20 minus, and then P we found to be 5. So that's 5. And then we still have this negative dp dt. So then solving this out, on this left-hand side, we have, looks like 90, and then this is 15 times 2, so that's 30. 90 over 30, that's going to be 3. So we find that 3, negative dp dt is 3. Negative dp dt is 3. We can highlight that. And now I think we have everything that we need over here to solve for, again, we want to find what dy dt is, but now I think we have everything. So this is equal to, we'll put it in blue. This is equal to negative 240 times 20 minus, and what did we say P was? P was 5, and then to the negative 2 power, and we found negative dp dt to be 3. So this is 3. And all of this is dy dt. And home stretch, folks, here we go. So we have a negative 240 times 3, so that is negative 720. And then in our denominator, 20 minus 5 is 15. 15 squared is 225. And then let's see here. Can we simplify? 7, 2 is 9, so that can be divided by 3. And then this is also, can I divide by 3? 25. All right, so this can be divided by 9. This is 25 times 9 is 225. So this is 25. And then dividing this guy by 9, we have negative 80. And then this can be divided by 5 again. So we have negative 16 over 5 and feet per second. Feet per second. And that is dy dt. So just a little more than, it's roughly around 3 feet per second. So if we come back up here, let's just see. All right, so this is negative. We found that to be negative 16 fifths feet per second. And again, that's just saying our top of our ladder is approaching the ground at roughly, it's just a little more than 3 feet per second. So that's the problem.